So let us quickly start our session. Today's session is on the clock domain crossing. So this is very important, like when you deal with the multiple blocks, right, integrated together to perform a large functionality. So for example, right, ASIC design. If you take an ASIC design, you'll have number of blocks right within the design, and these number of blocks might have right different clocks. So when we have different clocks, so the problem is we have a problem of multi-clock domain. So now today's session is completely on right. I'm restricting this session to at the very basic level. So because I understand that it is to the faculty fraternity. So the scope of the understanding of in-depth knowledge is beyond the curriculums and all. So I thought like I'll restrict this session to the very basic session. So in this, like we are going to see the introduction towards the clock domain crossing, and we'll understand the basic terminology of what is clock domain, and so what are the different types of the clock domains we can have, and then so what are the clock domain crossing paths, and then we'll see the CDC errors, clock domain crossing errors. And for all these things, the critical is the metastability. So we need to identify like when these errors are going to come into picture. So we'll discuss that with the mean time between failures, and then how to mitigate these CDC issues. There are a few techniques like where you can overcome this, and so the reconvergence is one of the important the factor, and verifying with the CDC synchronization. So now this clock domain crossing is a bit challenging because we cannot identify this when we verify it through some simulations. So when you write a piece of code, when you design it, and then like when you simulate it, so these are the things which you cannot identify them. So that is a big problem. So only when you go to the post silicon, so then only it is possible to identify these errors. And these are the rare errors, like, so we don't know, right? It might be after 1 year, or after 6 months, or after 2 years, or after 1,000 years, right? It might arise. So what is the possibility and how to reduce these errors? So that is the key agenda of this clock domain crossing. So first, let's quickly understand the basic terminology of the clock domain. So there are two different types of clock domains. So one is the single clock domain, and the other one is the multiple clock domain. So when it comes to a single clock domain, so the complete the block is going to have different subblocks, and all these are connected with a single clock. So when a block is connected with a single clock internally, so then we call them as single clock domain. And the same thing, like when you go and integrate, let's say for example, if you take a few blocks. So there's a block A, block B, block C, and block D. So now when we go and understand this sort of picture. Right. So here, now when you have 4 different blocks, and if all these blocks are interconnected to each other with the same clock, so then we call them as single clock domain. If the block A, block B are connected with one clock domain, and block C and block D are connected with another clock domain, and the data signals are crossing between these two. So then it is called multiple clock domain. So your block might have a single clock domain, or it might have a multiple clock domain. So when you take an SOC or when you take an ASIC or any FPGA related, right, the blocks, in each and every block you have a different right sub-blocks which are integrated together to perform a particular functionality. So when these blocks might have a complex logic, or it might have a lower complex logic or mid-level complex logic. So when we consider all these three scenarios, so one might require a different frequency, and the other might require a different frequency, and the third might require a different frequency. So when you are integrating these three, and if the data is transferring between these three, right, blocks, so then there is a multiple chances or the more possibility of getting the data loss. So that is what the CDC problems are. So now if you look at a single clock domain, right? So now if you look at this particular structure, this is some particular logic that we are triggering. So let's say combinational logic, and we have two flip-flops, and this right, everyone, it's a clock divisor, and so the same clock is applied. So the source for for this is a single clock. So this is called a single clock domain. So when you have this sort of scenarios, so we generally call it as single clock domain. Now, even if you look at the divisor clock, right? So it is a clock divided by 2. So this particular clock is going to be the clock divided by 2. And if you look at the overall, whether it is a rising edge or a falling edge, so both will sync at the same time. So now if you see here, so this particular case is having the same falling edge, and even here also in this scenario also, like you have the same falling edge. So if they are in sync, then we call it as a single clock domain. So if you have a single source, and even if you go with a divided by clock, so f by 2 or f by 4, so then at what particular edge, so both will be in sync. So these are called single clock domains. So when we go to multiple clock domains, here it is completely different. Now the same combinational logic is triggered with the clock A, and let's say it might have a frequency of f1. So let's say this is 10 hertz or 10 kilohertz. And if this clock is operating at some 10 megahertz. Now if you look at these two clocks, and these two clocks are used for this logic. So that means this combinational logic is going to be triggered with this at some particular frequency at one particular edge, and this might trigger at the other particular edge. So now if you look at the same diagram, so here it is triggering at this point, and at the same time, so this is somewhere else. So now if you look at these two edges, the clock B is not into the picture, but the clock is now you can see the same thing with respect to clock B also. So when you have two different clocks, so both the clocks are in not sync, and so they can trigger at any instant of time, and because of which it might lead to an issues. It is simply like in a group of discussion like this. So I'm delivering and you people are listening to the sessions, and if each and everyone is talking to each other, so then there will be a loss of data. Whatever I'm going to deliver, you'll not be in a position to understand, because there are many triggers around you, so which is not possible to have a clear understanding on the session. So this leads to a data loss. So that is what is going to happen even in the multi-clock domains, where you have a different blocks, and each and every block is triggered with a different at different edges and at different frequencies when they are operating. So then each and every block will respond at different intervals of time, and the expected times, the expected expected data arrival time might be different, and the actual arrival time might be different. So when we have these sort of things, so then there's a possibility of violating setup and hold times. So when you have they violated the setup and hold times, so then definitely you have a possibility of losing the data. Now let us understand more, right, in terms of right, what actually the CDC errors are going to be. So as we discussed, right, it is going to be an unpredictable loss of data. So if it is predictable, then we can make some arrangement to, right, to avoid the loss of data. So if something is unpredictable, so it is not in our hands and it is not in our control, right, to avoid the loss of data. So here, the when we are not able to, so the only possibility to avoid this is to avoid multiple clock domains. But due to this, right, increase in complexities of the designs and, right, especially, right, SoCs, system on chips. Earlier we used to build, right, different blocks we used to integrate on PCBs. Now, right, we are integrating the same thing on a single die, on a single chip. So that is where, like, so we'll see all the SoCs. Snapdragon, for example, right, is an SoC, which consists of all the blocks which are required for a mobile communication. So, and each and every block, either it might be your GSM module, or it might be your GPS module, or it might be your memory element, or it might be your processing unit. So all these might operate at different frequencies. You cannot expect all blocks to operate at the same frequency. So here we cannot avoid them. So multiple clock domains in a few scenarios, right, is mandatory, and we should have these multiple clock domains. So then, right, what is the alternative for this one? So what sort of errors that we might get, and how, right, so we'll have a loss of data. That will quickly, right, we'll see in this one. So CDC problems, basically, they are going to corrupt control or data signals. When you look into, right, any RTL design, the RTL design basically is going to have two paths. One is called a control path and the other one is called data path. So when you take a multiplier, or when you take a, right, a UART, or when you take a USB, right, or any complex design, so you'll have a data path and you'll have a control path. So these two are different. So, right, there are two mix of signals. One is you have a control signals, and the other one, right, you might have data signals. So most of the times the control signals will try to trigger the data path. So that means, like, you have a control signals which might operate at different frequencies, and data path might operate at different frequency. So when you are transferring your control signal to a data path, so this might lead to a clock domain loss. So here this might lead to a corrupt in the control signal. Let's say, for example, if it has to trigger it, right, just before the right, or just before the edge of the clock, it should be stable, and it is not stable. At the edge of the clock, it is transiting. So this might lead to a corrupt in the control signal, or it might be a corrupt in the data signals. So it is unpredictable. And the most important aspect is the respins, because respin, in the sense, like, when you go through the 4 to 5 steps in a complete design flow, and after, like, say, after the post or after routing, so if you identify there is an issue in the clock domain, right, and after STA, if you STA is anyways, like, it is not going to detect the asynchronous behaviors, so we'll create all of them as false paths. So when you detect at later stage, right, before you go to the tape out, so the coming back to the design and then modifying your design and then again verifying it and then again passing through all these, right, all these steps, we call it as a respin. If the right, if the interaction or if the revamp is between the two adjacent steps, then the respin will not be a costliest right task. But when you go to the right tape out, and if you come back again to the RTL, modify your RTL, and again simulate it, and then again redo all the synthesis, right, and the floor planning, placement, routing, CTC, if you do all these steps, then it is a costliest process. It is going to add a huge cost to the product. So in the industry, we should avoid, or in any design, we need to avoid, right, these respins. So the respins are need to be right, is the costliest one. And it might, so these CDC might lead to race wins. Are difficult to reproduce and debug. So these are right very difficult to debug, and this cannot be right figured out at the verification level, at the functional verification level that easily, right? So you need to go with a complex. So am I audible, guys?
Yes, sir.
Right. Thank you. Because I've seen a few. Okay. So so it is very difficult to write the debug at the functional verification level. And as the temperature or the voltage or the process variations takes place, right? So these CDC problems might also change because a small delay addition so might push right your data signal right to move into the timing window. So when it moves into the timing window, so that definitely right it will be a problem with the setup and hold violations. We'll understand the setup and hold violations a bit later. So will only occur in hardware, often in final designs. So when you integrate all these things at the block levels, you will not find, right, if you are operating with a single clock. And if you're operating at multiple clocks, then you might find at the block levels only. And when you are integrating all the blocks together to make an architecture, so then, yes, definitely these things will definitely come into picture. So traditional verification techniques do not work for CDC signals. So that's the problem that we have. So most of the errors we rectify, right? Or we'll debug and we'll find out all the bugs at the functional verification step itself. But when it comes to these CDCs, this is not that easy to verify with the traditional verification techniques. So we need to adopt the other methods of verification techniques. So like assertion-based verification and so on, we'll discuss. A CDC verification methodology is needed, right, to reduce the risk of CDC-related data errors. Now, so I'm talking about metastability, or like it might lead to a data loss. How this will lead to a data loss? What is a setup and hold time violations? And if you violate a setup time or if you violate a hold time, so then what we call it as? So generally we call it as metastability. And before we go on, right, checking with all these terminology, let's understand what is a clock. So as we all know, the clock, right, is a synchronizing element. So it should instruct each and every flop in your design to trigger at the same instant of time. So if it triggers at different instants of time, so there will be a loss of data. So a clock is a periodic pulsating signal. And so this might have a voltage ranging from right 5 volts to 0 volts, right? It switches from 0 to 5 volts, or from 0 to 3.3 volts, or it might be 0 to 2.5 volts also, depending on the type of voltage right, that we are using for the particular clock generation. So digital logic uniformly connected to the signals. So the complete logic in your system will be triggered and will be connected through this particular signal. It is just like acts like right a symphony conductor. So who will keep the complete logic right in sync. So that is the key of right the complete the clock. So if you look at any system, right, the clock is the major and the clock is very important. So if the clocking path is properly right designed, so then you can avoid most of these sort of issues. So now let's say, so every flip flop might trigger at the rising edge of the clock or at the falling edge of the clock. So all the flip flops, if they are triggering at the rising edge of the clock, so all are in synchronous with the respective clocking domain. So action happens across the logic at one specific point. So either it might be rising edge or it might be a falling edge. So now in this context, I have used a register. A register is well known as a latch or a flip-flop. And latch basically it controls whether right? And most of the times, like, so here there is another important point that I want to address, because like most of them, right, or it might be from the post graduation also. So the latch, basically we always assume that it is not the basic difference between a latch and a flip-flop. Most of them, like, they'll say that latch will have an enable and flip-flop will have a clock. So I'm sorry to say that both latch and flip-flop, right, are going to be triggered with a clock only. So here we have right, a confusion over here. So so that I want to address over here. A latch can be controlled with a clock, and a flip-flop can also be controlled with a clock. Only thing is, you have two sensitive things. One is level sensitive and edge sensitive. The latches will respond at levels, and the flops will respond at the edges. That is the only difference. Both are going to hold the data or register the data. So contain a transistor that trap the input value at the appropriate time. So either the trapping might happen at the rising edge of the clock, or it might happen at the falling edge of the clock. So the way you have designed the flip-flop. So how does this happen, right? So now this is very important to understand. So how a data is going to be registered, right, within the flop. First, we need to understand the flop, right? How right, it is going to latch the data at the transistor level. So if you understand at the transistor level, then we'll be understanding more at the right the setup and hold times, right? So now let's see, if you look at a simple the design of a flip-flop. Always at passage clock begin, Q is equal to T. This is a simple one. So there is no enable, nothing, right? I'm controlling only with respect to a clock. So now, whenever you have a passage of the clock, that means when it changes its state from 0 to 1, so then this always block will be triggered and the data will be loaded into the right a register. So now, let us have a quick look at the schematic diagram. So which defines the two latches which are cascaded together, and the first latch is operating at a clock is equal to 0, and the other one, or let's say clock, and the other one might operate at the clock pair. So if both the clocks are, and if both the latches are connected in this fashion, and if both the clocks are out of phase, so then it is nothing but a flip-flop. It is going to store a bit of information, and this is going to trigger only at the edges of the clock. Either it might be the rising edge or the falling edge. The circuit you have seen here is going to be only at the right, the pause edge of the clock. So now if you look at this one, so here this is the clock and this is the clock bar. So both are generated together, and these are the transmission gates. So, and these are the buffers which are connected together in the loop fashion. So now first let's understand, right, these two inverters. So now the first inverter is connected. Let's say this is the first inverter. And the output of the first inverter is connected as an input to the second inverter. And the output of the second inverter connected as an input to the first inverter through the transmission gate, right? So now here is the control. So if the transmission gate allows the data signal, then it will be in the loop. It will be in the loop. So this loop is going to hold the value. Is going to hold the value. So that is the key of right placing a transmission gate in the loop. So even here, so this is going to work as a latch. It's a simple latch which stores right one bit of information, and it is transparent right to your input at the levels of the clock, right? Okay, so now if you look at this one, when clock is equal to 0, this clock bar is going to become 1. When clock bar is 1, right, and the clock is 0, right? So this is a transmission gate and this is an NMOS, right? And this is a PMOS. So when these two, when the clock is connected to both of them, since clock is equal to 0, So this might be off, and this clock bar, so this might be off. So both the transistors are off and this transmission gate is in off state. So similarly, when you look at this one, so this is also the same thing. So here the clock is connected directly to these two transmission gates, and these two, right, will be turned off, and it offers a high impedance path, right? So when clock is equal to 0, the clock bar is 1. So the clock is equal to 0, clock bar is 1. When clock bar is 1, so this is going to be triggered, and this is also triggered. So these two transmission gates, right, will be enabled, and it will allow the data to pass through it. And if you look at this one, this particular transmission gate is already turned off, right? So now this data will pass through it. Let's say, for example, if your data is 0, this data 0 will be, right, flowing through this transmission gate because it is enabled. And this here we are going to have 1, and this will be 0. Now, right, after passing this 0, now if you turn on this one, if you turn on this, and if you disable this, so now let's say, for example, if you are disabling this one and if you are enabling this, so then this 0 will pass through this and this one. So this loop will continuous, and it is going to hold the value. So this is how the latch, that is, right, is going to hold the value with the help of the transmission gate. So this is the first thing, like, so how a latch is going to hold the value. Right. So now the data is passing. Now this is holding the data. Now if you look at this one, I've changed the clock signal from 0 to 1. And when the clock signal has changed from 0 to 1, so then this 1 is going to trigger these two transmission gates, and this disables, right, these two transmission gates. So when it has disabled the transmission gate, it doesn't allow the data to pass through this one, and this latch is already holding the data, and the data that is, right, held by this first latch will be passed through the transmission gate, and then so now this latch starts, right, holding the data. So in the first one, so the first latch is holding the data, and when you are, right, providing clock is equal to 0, so then clock bar becomes 1, and these two transmission gates, that will again turn on. So now the second latch will hold the data. So for this whole period, your data should remain stable. If your data is not stable, so then definitely you'll have a problem, right? Because, right, you are trying to write a logic 1. You're trying to write a logic 1, let's say, or logic 0. So then it will hold the data. By the time it writes into the second latch, if a new value comes over here, if a value changes from 1 to 0, so then it starts, right, changing the data again over here. And by the time it captures this, by the time this latch captures this value, so again, it might capture some other value than the previous value. So this way will, right, so we'll lose the data. So this is where the capturing is very important, and the holding the data for this duration is very important. And this time, right, we generally call as the timing window. So during the rising edge and the falling edge, so just before the clock edge, we should maintain, right, the data stable, and even right after the passage also the data need to be maintained a constant. So this is called, right, a clocking window. So if the data is stable during this clocking window, so then definitely you can avoid the setup and hold violations, and which can avoid the metastability issues. So this data has a good, right, so if you look at this whole setup of the register, right, so it only works if the data has a good value at the rising edge of the clock. So that is when there is no setup and the hold violations. So now the data is perfectly latched in the first one, and the data is maintained stable, right? And then so it leads to a perfect latch in the second latch, and then finally you can capture the response from the right output. So basically, any flip-flop is a cascade of two latches, right? And both the latches are level sensitive, and when they are connected together, your output seems to be right changing at the edges of the clock. And during the edges of the clock, your data need to be stable in order to have a proper data at the output and in order to avoid the loss of data. And this latch avoids the metastable issues. So what is a metastability? Metastability is nothing but violating the setup and hold conditions. Now you can see here, so there's the clock and there's the clocking edge. So during this rise edge of the clock, your data is stable. If this data is stable, right, let's say for example, if you are getting a data like this, so during this window, your data is 1. So it is stable, it is not changing. So if it is not changing, that means it is passing the complete setup and hold times. So therefore, we can avoid the metastability issues. On the other side, if it doesn't maintain constant during this window, and if it changes like this scenario, so then it might fall into violations. So when it violates, and you'll get an unpredictable storage in the device. So this leads to a metastability. So when setup and hold conditions are violated, the output of a storage element becomes unpredictable. So what is mean by unpredictable? So unpredictable in the sense when you are capturing the data. So when it is writing, when it is rising, you are writing the data. So when you are capturing, your data might be right at this level or it might be at this level. You cannot predict whether it is at logic 0 level or at logic 1 level. So this is what we call it as, right, metastable state. So how to avoid this, and like what is the frequency of this metastable state? So the frequency of metastable state can be figured out through mean time between failures. So it will tell you, right, what is the frequency of the failures because of this, right, phenomenon. And this is right is defined as, so 1 over f clock into f in. F clock is nothing but your clock frequency and your data signal, and then duration of the critical time window. So this one, right? This is the timing window. So it all depends on your clock frequency, how your data is changing, right? The frequency of your input, and and at the same time, like what is the timing window? So what is the duration of the timing window? So based on this, we are going to define the mean time between failures. So if it is not contained, right, metastability can propagate. So if you are not containing in one flop, so let's say for example, if you are going for a right shift register, right, where we are going to connect the one stage output to the next stage and so on. So if you are not containing in the first one, there's a possibility that the second flop might also have the same issue, and the third flop might also have the same issue. So if it is not contained, so there's a possibility of right propagating this issue. So metastability is unavoidable in designs with multiple asynchronous clocks. So as we discussed, so there are right in each and every ASIC or SOC, you have different blocks, and those blocks are going to be function with a different clock frequencies. So that we cannot avoid. So metastability also we cannot avoid. So only thing is the frequency we can reduce. That is the only possibility. So what are the ways of right reducing this frequency, and what are the ways of right avoiding this metastability, and how to detect this? So these are the next concept, right things we need to understand in detail. Clock domain crossings guaranteed to cause metastability. So there is no issue, and as we discussed in the previous one, so we cannot avoid them. So we will get these metastable issues. So when we get these metastable issues, how to detect them and how to avoid them and how to reduce the impact of these metastable issues on the designs. So that is the only thing that we can do. So when two or more designs run on disparate clocks, so means, so on a disparate clocks in the sense like when you have two clocks with a different skews or different frequencies or different phases. So naturally, this is going to arise. The clocks will continuously skew, guaranteeing setup and hold violations. Skew is nothing but a delay. So when the clock is delayed, so then definitely, right, it might get into a setup and timing window violation. So therefore, it might lead to a clock domain crossing issues. Signals from one clock domain, right, moves into another clock domain. So this is another possibility of, right, getting metastable issues. And there's the largest possibility when you have multiple clock domains. So you'll have these metastable issues. So for example, if you look at this one, in this particular scenario, we have two flops, and and these two flops are connected together, but the two flops are triggering with the two different clocks. So one is a sensor system and the other one is a guidance system. So in the sensor system, the clock is operating at one frequency, and this is right at a lower frequency, and the guidance system is operating at a higher frequency. And there is a data exchange between these two systems, right? So that is clearly represented clock domain crossing signal. So now since these two systems are operating at two different frequencies, now both the flops are going to be triggered at different points. So when both are triggering at different points, so then let's say for example this has triggered at this point and you got the data, and after some time your second latch or the guidance system is triggered. So that means by the time the data is available and by the time it triggers the second guidance, that is guidance system, so at this edge the data might change. So when the data changes at this edge, so then it leads to again metastable issues, violating setup time, right? That is timing window. So if it violates the setup and hold times, so then definitely it leads to a metastable, right? So then it leads to an unpredictable scenarios in the capture, in the response. So now let us take the same thing in terms of two clock domains. So now if you see both the clocks, clock A and clock B, and so there is a transmission signal that is moving from the clock A to the clock B, right? So the clock A domain, and now if you see here at the level of the clock, and the data is changing, but at the edge, the clock for the clock A at the edge, so the data is stable, right? But when you look at the clock B, right, the same data is changing at the rising edge of the clock. So this leads to, right, violations for the setup and hold. So now this might lead to a metastable state. So signals that cross asynchronous clock domains will violate setup and hold times. So here we need to be very careful when you are moving from one clock domain to the other clock domain, right? So this is one scenario. So what sort of problems we'll get, right? So let us look at mitigating clock domain crossing issues. So what are the problems that we have identified? Signals crossing a clock domain will violate setup and hold thing. So that's the first one. So what is the impact of this one, right? If you look at this, right? So there's a loss of data because, right? So the same data need to be captured over here, but we are unable to capture the same data, the stable data, right? Because the data is changing, right? At the capturing edge of the second system, right? At the second clock. So therefore, since it is changing, right, within the timing window, so it violates either setup or hold. So when it violates either setup or hold, so definitely, right, the captured or the response of the second system might go into an unpredictable state, right? So this is one possible way of getting into or losing the data. So the impact is going to be either you might corrupt the control data or you might corrupt the data signals. Now in this, right, if you look in the previous scenario, so here there is a transfer of data from one clock domain to another clock domain. So a sensor system, right, has detected something and it has transmitted. So there's a, right, basically a control signal which is passing from one system to the other system, or it might be a data, so which is going to a guidance system. So there might be a loss of either a control or data signals, so which might lead to a loss of data. So what are the approaches that we have? So how to avoid this, right? Avoid having systems that have multiple clocks. Is that possible to avoid multiple clocks? Right? It seems to be sensible, but it is impossible. So we cannot avoid multiple clocks. So that is right. That is one thing we should not expect from the designers. So now what we have to do? So okay, fine, we cannot avoid, but what is the alternative to this one? So how to address to this issue? So design around the problem. So now where is the problem? Sorry. The problem is around the second system. So while you are capturing, right? So if you look at the previous one, so the problem is right somewhere over here. So we need to safeguard this one, right, in such a way that we should get the stable data instead of an unpredictable data, right? So now what we have to do? So we have to safeguard. So we have to put a guard, right? We have to put a fence, right, across the problem. So that is how we can avoid. Okay. So designer can add synchronizers to the design. So the best possible way is to add synchronizers. So we have different types of synchronizers. We'll see. Metastability still happens, but nobody else sees it, right? So only thing is, because we are going to safeguard or we are going to fence it, we are going to hide it. So now if you look at this, right, the particular scenario, so this first one is operating is a transmission domain, and this is your receiver. So this is your transmitter and this is your receiver. Your transmitter is operating at a TX clock and your receiver is operating at a RX clock. So now here, and since the transmitter and receivers are at different right complexities and they are operating at different, because of which they might operate at different clock domains. When they are operating at different clock domains, so how best we can avoid this is to put a synchronizer. So how this is going to avoid, right, this particular metastable issue. So now let's say, for example, if there is a capture of the data. So let's say the data is captured. So now this is the data that is passing through this one, right? And so we have observed that, right, when you have a single flop, right, which is capturing the response. So then, because these two are operating at two different frequencies, this might lead to a metastable state. So when you say metastable state, either it might have a logic 1 or it might be a logic 0, right? It might not be matching with your data. It might match or it might not match. So, or it might be in between these two. So it is an unpredictable. So to figure out whether it is a logic 1 or logic 0. So now, earlier we used to have a single flop, right, to capture the data from the transmitting end. Now you have, right, two stages which are connected together and both are triggered with the same RX clock. Now here, this is an unpredictable nature. This data is having unpredictable nature. Now, if you look at this one, it's a two-stage, it's a simple shift register. So now in the next clock edge, so if you look at this one, so the first flop will be triggered at this clock edge and the second flop will be triggered right at this clock edge. So now the first flop has captured the data, captured this data, and this is the response that we got from the first flop. And so we have identified that the first flop is having an unstable or unpredictable data. So now this data is captured by this one. So by the time it reaches to this right stage, so this data might get a proper stable value. So now if you can spend right one clock cycle more, then there is a possibility that you might get a stable data. So at an expense of one clock cycle, so there is a possibility that you might get a stable data at the receiving end also. So this is called two-stage synchronizer. Now is this receiver right receiving the unstable data or unpredictable data? No. So what is the data that we are capturing at the arrival at the receiving end? So it's a stable data. Earlier, so we used to have only one flip-flop where we used to have an unpredictable data. So this might lead to a data loss or a metastable or setup and hold violations. So now this is completely avoided. Now this receiving end cannot see this this unpredictable nature, and this is going to be hidden under a fence. So we are creating a fence throughout this, and this this unpredictable nature is not seen by this receiving end. So the receiver still is going to capture the stable data. So this way we can avoid the metastable condition. So now what is the advantage with this one? If earlier in the previous design we have seen a transmitter is directly connected to the or a sensor system is directly connected to a guidance system. So where we have faced this issue, and so the occurrence of this error is very frequent. So let's say, for example, the mean time between failure that is calculated in the previous case is 1 hour. Now, because of this setup, because of this two-stage synchronizer, it might extend to 1 lakh years. So that means in the lifetime of the product, so you might not find this error. So that is the advantage that we have with this two-stage synchronizers. Designers add synchronizers to reduce the probability of metastable signals. So here we are not avoiding the metastability, we are reducing the probability of occurrence of this issues, the setup and hold violations. Synchronizers are subcircuits that can prevent metastable values from being sampled across the clock domains. Now, what is the problem with this one? So we are able to prolong this failure. Fine. So we are able to postpone this to a later stage. At what cost? At the cost of an additional synchronizer. So this is not a part of the logic which is involved with the design, and we are adding few more the flops additionally with this one. So this might lead to a disturbance in the clock, so that the clocking frequency that need to be adjusted properly. And so this adds an additional the gate count to the design. So take unpredictable metastable signals and create a predictable behavior. So the first simple technique is to provide synchronizers between two different clock domains. So now the same thing, if you look at the clock A and the clock B, so now let's see, the transmitter has transmitted the data. So now there's the signal, and so if you see here, metastability issue is there because exactly at the edge, so the data is changing, So now the Q is going to be into some unpredictable nature because this is already into the metastable state. And when you look at this one, when you look at the RX data, so your data is stable, So the first one, will receive a stable data, and at a later stage, the second flop will also receive the stable data. So by the time it reaches to this register or to this design or a block, so your data is stable. So this is how we can avoid the metastable states. So by simply adding synchronizers, so we are not completely avoiding this, right? Or we are not completely rectifying these issues, right? What we are trying to do is, so we are trying to, right, reduce the occurrence of, right, this one. So that means we are prolongating the occurrence of this error. So that is a mean time between failures. So earlier it might be 1 hour or 2 hours. So now because of addition of these synchronizers, so it might lead to 10,000 years or 1 lakh years or whatever. So here we have one more, right? So point to understand. So if you just a minute. Okay. So now synchronizer delays can reconverge with unexpected results. So we have added a synchronizer, and the synchronizer might lead to an unexpected results. So for this, like what we are going to do is, right, we are going to use a reconvergence technique, right? So here, so we'll develop a separate the control signal and the control FSM. This control FSM is going to, right, control all the transmission data. So TX D0, TX D1, TX. These are all different data which are right traveling from the transmission block to the receiving block. And by using this FSM, right, we are going to synchronize these, right, the data which are available at different stages, which are violating the metastable conditions, right? These are properly synchronized with an FSM. So so as it is shown in the figure, I'm not going much details into the design. So it takes a lot of time to understand, right, the complete design of this FSM. So CDC signals cross with an unused relationship, can be combinational, or it can be sequential, or it can be deeply sequential. And so when you have these delays, right, so now, for example, if you look at the previous one, so these are all going to add the delays. And as I said, like, so it is going to disturb the overall frequency of the system. And so this might lead to a few more errors. So in order to avoid that, so we are going to add this, right, the control FSM, and this is going to right solve these issues which are caused by the synchronizers to an extent. Now, if you look at this one, this is adding additionally, as we said, like, so these, to avoid this metastability or right, to prolong this occurrence of these issues, so we are adding two-stage synchronizers. So by adding two-stage synchronizers, so we are getting a few more issues, right, which are related to the delays, and this, right, we are trying to avoid by adding an additional logic along with it. So by creating a different state machine which controls all these data, and these synchronized data will be passed to the right receiving ends. So CDC signals cross with an assumed relationship. So now, earlier when we started our discussion, so it is completely an unpredictable right system. Now, by adding synchronizers, we have made it right to prolong to a few more years, right? So the probability of occurrence of these issues have reduced because of the addition of the synchronizers. And since these synchronizers are adding the delays, so it might lead to some other problems. So these problems can be rectified through reconvergence technique, and this can be right avoided. This can be generated through some control FSMs, right? And these control FSMs will add the hardware, additional hardware, along with the synchronizers. It will be an overhead on the design because it is not contributing anything to the logic. So therefore, consumers, for a consumer perspective, right, this is an additional logic that is added into it. So it's an additional cost for the right. But we are able to predict the behaviors. So we are changing from an unpredictable nature to the predictable behaviors. That is the right beauty of this reconvergence. Unpredictable delays on CDC paths leads to reconvergence errors. So designs need to logic need logic to correctly handle reconvergence. Can occur on a single bit or multiple signals. So when you are passing the data, right? If you look at this particular data, now when you are synchronizing, so this data is corrupted. If you are carefully observe, this particular one is changed to 0. The rest are all the same, and this might lead to, right, a metastable condition. So this might lead to an error. So now the same thing, right? If you go with this technique, right? So when you add a gray decoder, right? So then you can simply avoid it. But it is delayed version. Yes, it contributes as synchronizer contributes to the delay. This will also contribute to a delay. But what we can assure is it's a valid signals are passing through, right? Passing to the right receiving ends. So that is the advantage that we have, right, with this technique. So now, so this can also be, we don't have only one technique, so we have multiple techniques with this, right? So we have multiple techniques with this. So when you are adding these synchronizers between two different clock domains, so you have to assure the predictability. So that is what like we are trying to do. By adding synchronizers, we have, right, we have prolonged the issues, and after that, like by adding few more, right, additional logic, that is FSM and then gray decoders. So we are making sure that it is predictable. So how do you make sure that it is predictable? So by simply adding synchronizers, it might not, right, be sufficient. So what are the other protocols that, right, need to be verified? So here, synchronization between the two clock domains requires a set of protocols. So to ensure the predictably transferred the data between the two clock domains. So these protocols must be verified. So who will verify it? These must be verified at, right, the functional verification step. So how we are going to verify this, we'll see, right, with few more, right. There are some additional techniques. We are not going to in detail into those techniques. Let's understand what are these techniques. When the protocol is violated, so what is the protocol that we have kept, right? So the previously we have added synchronizer and an additional logic. This is the protocol, and that protocol, it should make sure that there should not be a data loss, or it should make sure that there is a predictable behavior. Simulation may not show a failure, so silicon will eventually show a functional error. So when you do a simulation, right, with these things, right, it might not show an error, because when you fabricate it, so each and every layer, each and every set of layers will contribute for an RC, right, and this might lead to a delay. So you'll have a wire delays, you'll have a gate delays, right? So you'll observe an additional right parameters that are, right, added to expected things. So at the simulation level, we always expect to be, right, running at a zero simulation times. So therefore, we might not predict. And when you go and verify on the silicon, so then these errors might, right, invoke, and these leads to a functional errors. So synchronizers won't function properly if the required transfer protocol is violated. So by simply adding synchronizers, we cannot make sure that, so this is going to be completely, right, avoided. So what else we require? So here, first the verification environment. So whether it is assertion-based verification or, right, the formal verification techniques if you adopt, right, this has to make sure that it should cover three problems. So the first one is the missing sync problem. So what are the signals that are, right, are missing the synchronization? So that first we need to identify. The second thing, right, the possible protocol problems. So when you are adding synchronizer, so as we discussed, right, it might add, it will add definitely a delay to the path. So when it adds delay to this particular path, so then how this, right, you must be in a position to identify those errors, and we must address, right, to those errors in the design. If not, so these errors will, right, again invoke when the product reaches to the customer, and it will degrade the performance of the product. So it in turns affects the company's performance. So this is the second issue. The third issue, the third issue is on the addition of these two-stage synchronizers or three-stage synchronizers, so which we have added. So that might lead to a reconvergence problem. And this reconvergence problem, anyway, like we are adding right with FSM and we are trying to control. So this also we need to identify. So only when you identify this, there is a reconvergence problem. So then only we have to add this, right, the remedy for this one. Otherwise, right, at each and every stage, if you keep on adding this right FSM circuitry, additional logic, so it will be an overhead to the design. So this first you need to identify, and if there is a high potential of this problem, so then these rectification techniques need to be adopted at the respective stages. So these bugs need to be identified at the verification level. So clock domain crossing needs structured synchronization. So structured synchronization, transfer protocols, global reconvergence checking. So when you go with a structured, right? So for example, so how do you make a proper synchronization? So now if I'm delivering and if you are also shouting something, right? So there is no a proper understanding between the two parties. So when I'm delivering, you are listening. And when I stop my delivery, if you start right questioning, so then, so definitely there will be a proper exchange of data between the two parties. So that is what we need to make sure. And this is called the protocol. So how do generally we follow the protocols in the communication systems? So first, we'll send a request. We'll send a request, and the receiving end receives the request, and it sends an acknowledgement, right? And the transmitting end, now it transfers the data. So these are called handshaking signals. So you need to have a proper protocol, right, between two different domains which are operating with two different clocks. So these if you follow these protocols, then definitely you can avoid the data loss. So in the scenario that we have discussed, that why we are following that protocol of right sending a request and then waiting for the acknowledgement and then transmitting the data, and then again, right, the receiving end will acknowledge that I have received the data. So this whole protocol is to avoid the loss of data. Is to avoid the loss of data, because there are many right many receivers, and any receiver can right take this broadcast, but our intention is to right to a particular receiver, and that particular receiver should respond. If that receiver is not in a responding position, then will not transmit the data. So if it is a broadcast, you can broadcast it, right? Whoever wants to take, you can take. So the protocol is not required when you go for a broadcasting. But when you are transferring a data between two peers, so then definitely you should have a protocol, a proper protocol between the two peers, so that you can avoid the loss of data. So the same technique, right, we should also adopt, right, even, right, in the CDC, addressing to the CDC issues. So the problem, signals crossing the clock domain, so will definitely violate a setup and fault. So as we discussed, right, the big impact is on the control and data signals. So it will be either dropped completely or it might be corrupted. So we have seen the approaches also, right? So designers should add, right, a synchronizer plus full CDC verification. So we have discussed so far, right, on right adding synchronizers, and synchronizers might have an additional problems created, and that problems can be rectified. So reconvergence errors, and these reconvergence problems can further be rectified by adding an additional circuitry, right, either through the gray code FSMs, right? So this makes sure that the metastability or mean time between failures, right, is increased. So we are not completely avoiding, and by adding these reconvergence technique, or the reconvergence problem can be rectified by adding additional logical circuitry through FSM controls. So that will make sure that you have a predictable nature. So with this, we are adding the predictability to an unpredictable behavior. So assure synchronizers are present and used correctly. So how we are going to make sure that they are operating correctly by addressing to the reconvergence problems. So what are the recommendations that we have, right? So in this, during the design planning, we need to create systems and designs using one clock and one edge when possible. So simply you cannot design you cannot design systems with a multiple clocks, right? So that always you should avoid, and you should have to make sure that if unless and until if it is mandatory, so then only you have to go for a two blocks which are operating with a two different clocks. Otherwise, you have to make sure that all blocks are going to be triggered with the same clock domain. So what generally we do is like we are going to adjust with the clock with the timing, right? And so based on this timing, we'll add some delays to make sure that both are going to operate in the same way, right? And we'll make sure that all the blocks are going to operate at the same frequencies. In some scenarios, so we might not be in a position to address to these we cannot avoid right with a single clock. So that is not possible in some rare cases. So we cannot make sure that complete block is going to operate with a single clock frequency. So in such scenarios, right, it makes mandatory so to operate with the two different clock domains. So if that is the case, then we should go with the additional techniques like adding synchronizers, right? And we have seen a simple two-stage synchronizer. So we can also add the flop. So an additional flop three-stage synchronizer is also possible. And we can also go with a 5/4. So first in, first out also we can use. That basically the first in, first out can be used between the two different clock domains because it is an interface between a read clock frequency and a write clock frequency. So one clock domain might operate with one frequency and the other clock domain might operate with another clock frequency. But when you add FIFO, it adds a lot of the additional logic to it. So we have to make sure that if you can overcome this issue with a two-stage synchronizer, it is well and good, right? And if it is a critical issue, so then definitely, if let's say for example, if one block is operating at 10 kilohertz and the other one is operating at 10 gigahertz, so then these two-stage synchronizers might not help. So therefore, we should go with the complete FIFO design. So which need to be calculated with the FIFO depth. So based on your write frequency and read frequency, and so accordingly we'll consider the memory that is required to store this data. The write frequency write the data, and the read frequency it might operate at a different clock, and this might read at a different frequency from the same memory location. So this is another recommendation along with the two-stage synchronization. Right, if you have an issue. If multiple clocks are required, try to use one designer for both clock domains. So this is the challenging thing. So when you are, let's say for example, in an ASIC or in an SOC, you have different blocks, and each block will be distributed to different RTL design engineers. So if one is designing one block and the other one is designing another block, and these two blocks are having a clock domain crossing. So then the first designer might not understand, and second designer might not understand. If the whole, if both the blocks are designed by the single designer, right? So then definitely he can address to this issue, right, at the designing level itself. So that is why it is right. It is a recommendation that if you find any multiple clocks, right, are required, so for a particular block or between two blocks, so then definitely you should go for a single designer and make sure that all the coding guidelines are followed. So use signal naming conventions. This is another important. So let's say, for example, there are like so 4 designers working on a single right project, and in this, like, you have multiple blocks which are with a multiple clock domains. Right. So I've designed one block and the other one is designed, let's say, transmitter and receiver, the same thing. Or if you go with the same example of the guidance system and the sensor system. So I've designed a sensor system and some other has designed a guidance system, right? So we should understand that this is coming from a different clock domain. So how do you understand? Right? By looking at your inputs. By looking at the interface signals, you must be in a position to understand, right? Okay, so this particular block is having an interface from a different clock domain. So this is possible only through a proper naming conventions of the signals. So now let us understand this one. Now, when you are designing these different blocks, right, which are having multiple clock domains, so then simply append underscore a underscore range means, so this particular signal is coming from the block A or the register A. So append underscore a underscore h to signals leaving a clock register. So it is saying that from a clock register, right, these signals are transferring. So underscore a for a clock combo signals. So leverage during code reviews, help identify missing synchronizers. So in this way, like, what we can do is, right, by proper naming conventions, so we can also make sure that the other designer can also easily understand. So these are the synchronizing elements. These signals must be properly synchronized. If they are not properly synchronized, so we are going to face a metastable issues. It might violate setup and hold times. So therefore, the designer will understand and he'll make sure that proper synchronizing methods are applied across these clock domains. So make sure only a read signal go to the synchronizers. So now if you look at this one, so my signal TX transmission, so it has passed through this clock domain. So this is clock A, right? Or the transmission clock. So my data underscore TX underscore reg. So in this previously we have discussed that underscore A underscore reg. So now we are changing this to my data underscore TX underscore reg. So now this is making sure that this block designer will understand that, so it is a synchronized signal, and when they understand it is as these signals need to be synchronized properly, so then they'll go and apply the synchronizers, a two-stage synchronizer or a FIFO, so whatever the synchronization technique so that they want, so they can simply apply between the two clock domains. Okay, so this is a proper naming convention that need to be followed. So even from the first register, we have RX sync 1, and from the second synchronization flop, so we'll get RX sync 2, and this is so this is from the output of the combinational logic. Okay, so these conventions need to be properly followed. So if the conventions are properly followed, the designers at both the ends, even though they are designing a multiple clock domains, so they can easily understand that what are the signals that need to be properly synchronized and what are the signals which doesn't require any synchronization. Okay. So many clock domain errors come from design changes, but these are not at the initial stages of the design. So limit clock domain crossings to specific areas or blocks in the design, right, if possible. These techniques can help assure synchronizers are present, but are unlikely to help identify reconvergence or CDC protocol issues. This already, right? So we have discussed. So it might prolong the mean time between failures, but right, the reconvergence or CDC protocol issues might right further rise. When multi-clock design is required, so plan for proper verification. So when you see that a particular a set of blocks need to be verified, and if you identify these are operating at different clock domains, so then utmost care need to be taken right at the verification level, and the proper verification plan need to be adopted, and the proper assertions need to be developed right to figure out these sort of issues. So how to accomplish right this one? So verifying CDC synchronization. Missing right synchronizers will create a metastability. So that's right. We have right clearly understood from right this particular right examples. So if you avoid the synchronizers, then definitely you'll have either a data control, a data loss, or a control data signal loss. Correctly placed but misused synchronizers, that doesn't work. Reconvergence of synchronized signals can create unexpected behavior. So this need to be right addressed. This need to be converged. Approaches. Simulation is one thing. Digital logic simulators do not model transistor behavior. So do not model metastability. So that is not possible. Now, so when you look at a simulation, right? So if your data changes at the clock edge also, your simulator will respond. So now you can see, right? So we have got a response from the flop. The same data is latched, and so we got a response. So these are the simulation results. So what is the problem here? The problem here is the data signal has violated the setup time, right? So there is a violation in the setup time window. So and the setup time window is not properly figured out by the simulation environment. But when you do the same thing, right, post fabrication, so then you'll find so these errors. So post silicon, you'll find the error, but pre silicon, you will not find the error. That is during the simulation, right? You will not find these errors. So simulation captures a 1, right, while a silicon captures either a 1 or 0. This is called an unpredictable nature. Now, even if you look at the other way also, right, even post clock edge, right, if your data is changing, before the clock edge, the data is stable, so it has right the setup window, and post clock edge, it has violated the hold. So when it violates the hold, right, even in this case, it doesn't right figured out. And only thing is, like in the next clock edge, you'll get the stable data, right? So because the clock is errored and the data is changed post clock edge, so the flop cannot capture this particular data. And if the data is stable, then it might capture at the next stage, because setup and hold right while it has right a stable data before the edge of the clock as well as post edge of the clock. So therefore, right, there is no setup and hold violations. So right, you will not get metastability. So you will get the data, stable data. So there is no loss of data. Only thing is we have consumed an additional clock edge. This is fine, but so it is getting delayed, right? And if you make sure that for the next clock edge also, if your data is stable, so then there's a possibility that you can have the same data. So if, let's say, for example, in the same scenario, if your data is changed here, if the data is changed here, So then whatever the data you have here, that is lost. So why we have lost this data? So we have lost because, right, there is a violation in the setup and hold window. So because of this, we have lost the data. So here, since the data is holding the same value, right, even for the next clock age, so we are able to capture the data. But if the data is changing before the next stage, so definitely a new data will be captured instead of right 1. So you'll continue with a 0 because this is the new data that is latched right at this age. So 0. So it will continue with a 0. So these sort of problems will get right. So when you have the hold violations. So when you go and simulate the gate level netlist. So let's say, for example, if you go with the gate level simulations, so there's a high possibility of identifying these issues to an extent. So now you can see there is a predictable data even post silicon also you can see, but not at the same edge, but at the later stages. Simulation captures a 0, while silicon produces either 0 or 1. So when you have a setup and hold violations, your simulation environment or your verification environment might not capture these issues, right? So who will capture these issues? Like when you go and bring your design to the silicon level, so then you might capture these issues. So how to get this to an extent? If you go for the gate level simulations with the gate level netlist, which is generated post synthesis with all the constraints, and with the targeted technology library, and if you simulate this gate level netlist, then so there's a high possibility of detecting these sort of errors. So simulation does not reflect the functional simulation does not reflect the silicon behavior. So verifying CDC synchronization, missing synchronizers will create this already. So simulation environment will not model CDCs correctly to detect errors. So what you have to do? So static timing analysis. Will the static timing analysis adjust to it? Can be used to identify signals that cross domains. So this will help to identify the cross domain signals. Can be used as an input for a manual review, right? But won't detect missing or incorrectly used synchronizers or reconvergence. So the basic problem with the static timing analysis is even it cannot predict the asynchronous behavior. So static timing analysis is preferably for synchronization. If the blocks are completely synchronized, so then you can go and identify the setup and hold time violations in a properly synchronized system. If you have a multiple clock domains, so that is a clock domain crossing, and if you are going with the asynchronous behavior, asynchronous behaviors can never be addressed or figured out or identified. We cannot identify these bugs at the static timing analysis step, because all these clock domain crossings will be kept under false paths. So therefore we cannot predict the unpredictable nature or the setup and hold violations because of these multi clock domain issues at the static timing analysis step. Now, what is the alternative? So the alternative is the gate level simulations. So the gate level simulations is to identify the X behaviors that is unknown, like either it might be 1 or 0. And so the basic importance of the gate level simulation is to identify these asynchronous behaviors. So how do we get the asynchronous behaviors? Either it might be a change in the phase clocks, or it might have a different clocks which are operating in a single block, or you might get a scenario of two blocks which are operating with two different clocks, and there's a data transfer between these two clocks, and this leads to again a multi-clock domain crossing. So these issues can be addressed only at the gate level simulation stage. So you cannot figure out, right? So these effects, right, either at the zero simulation stages or at the static timing analysis stage. So manual design reviews. So the other possibility is, right, so manually you need to verify all these, right, errors. So error prone, when you go with the manual things, right, definitely, right, so when you go into the deep, right, sequential circuits, so it is very difficult to identify these right issues. So it is very consuming when you go with a manual verification. Typically only identify synchronizer structures, misses reconvergence, and invalid sync protocols. So the manual design reviews that you can do to an extent, but when it becomes a complex, so then it is very difficult to identify even, right, to manual reviews also. Evidence suggests at least some synchronizers will be missed. So the reconvergence errors, like you have a different, the things that you can add to the reconvergence. Right, so lab verification. So problem is intermittent, debug is impossible. SPICE simulations, it doesn't model transistors, right? So where will you get the SPICE tech? All right, these are the different things. So the target technology library need to be there. So if you have a target technology library, and if you have a proper constraints written to that particular design, and if you can figure out, right, then by doing a proper gate level simulation, by creating a proper GLS environment, and if you can run a GLS, right, then, right, definitely you will figure out, right, where are the setup and hold violations, and you can specifically concentrate on, right, the multi-clock domains, right, whether with a clock phase difference or with a, right, different clocks operated, so that we can to an extent easily figured out, right, in the gate level simulation. So identifies, right, all CDC signals, structures, and reconvergence issues, all connected, functioning correctly, creates reports for manual reviews. So these are all manual verification, right? Okay. So what are the things that we need to, right, apply during the design? So create system or design using one clock, or that's already addressed, right? And during the verification, watch for multiple clocks in the designs, and a proper care need to be taken, that with respect to the signals which are need to be synchronized, and these need to be properly addressed in the verification plan. Ask how CDC issues are mitigated. So the structural verification, protocol verification, and reconvergence verification is the three important steps that you need to adopt, right, during the CDC verification. So the CDC verification is a separate thing, so which you can identify, right, if you look at a Jasper Gold. So the tool that we can make use of it, right, to identify all these issues, and we can identify and we can address to these issues, right? And this tool is from the Cadence environment. Similarly, from other vendors also, you have different the CDC tools. So reports are very important. So right, so carefully observing the reports, right, is very important to understand. So these hidden issues, and these hidden issues need to be properly addressed, and all these need to be, right, properly verified, right, before the chip goes to the tape out. So if you verify, if you identify these bugs post silicon, so then, as I said, like so it is going to be a huge respin again. So this will lead to a complex problems. So every multi-clock design is subject to metastability. Traditional verification methodologies cannot assure robustness. To properly mitigate these right, dangers of CDC, we strongly recommend a solution that supports manual reviews, right? So you can go with the GLS gate level simulations, automatically report all sources of CDC problems, has proven CDC verification and methodology, and the customer service. So this is right. So now I think so I have a lot many questions to address. Okay, so let me go through so one by one, and then I'll take up with the oral questions. So let me address this.
So shall I? Okay. Thank you, sir. Thank you for your insightful presentation. You packed in a lot of information into a short time and left us with concrete strategies. Thank you so much, sir. So now we will be posing the concerns of our dear participants. So I would request you to please do respond concisely, sir. So shall I go ahead with the questions, sir?
Yes, yes.
Thank you so much, sir. Sir, just for information, could you please name some protocols and how can they be verified?
So these protocols are like handshaking protocols are there, and so you have before that is already I have attested that, but I have not shown in the presentation. So you can go through some handshaking protocols, and so we have FIFO, so that can address to these the protocols.
Okay. Thank you, sir. Thank you so much. So, sir, is it possible to test these issues in like other simulators, like for example, Vivado or Verilators?
So you have a Jasper Gold from Cadence, right? So where you can address to these, you can figure out these issues.
Okay, sir. Thank you.
And we have the other from the Questa CDC is also there, and Spyglass from Synopsys. So if you can make use of these tools, yeah, definitely you can figure out these issues. And so at the end, when you go with the static timing analysis, so these are a bit difficult to figure out.
Okay, sir. Thank you. Sir, could you please explain a brief as about what is this? What do you mean by this deeply sequential circuit?
So deeply sequential circuit. So in the sense like when you have a huge number of states which are running, and a huge set of flip-flops are are synchronized. So then it might require a large number of clocks, to get the complete response. So it's a complex sequential design.
Thank you, sir. Metastability can be avoided in synchronous circuit with additional clock. So is it affecting the other parameters like power?
So the power might not be affected, like the frequencies, might affect. So these frequencies, see, that is what we need to figure out, before we pass the final gate level netlist, we need to figure out all these issues, and we need to add the flops, and finally we need to set the frequency. So the frequency will be an impact because when we have designed a circuit, so either the two-stage synchronizer or reconvergence logic to avoid the reconvergence errors. So these things, we are adding additionally to the functionality. So these are not the functional blocks which are contributing to the actual specification. So when we add these things, so definitely there will be an impact on the frequency.
Thank you so much, sir. Sir, could you please mention and familiarize us with some of the CDC tools?
CDC tools that's already addressed. One is Jasper Gold, and the other one is Questa CDC. And so you have a Spyglass from Synopsys. So these are the tools that we can use for this CDC.
Thank you, sir. Sir, could you please tell what do you mean by this control bugs, and could you please explain in brief about it?
So, so control bug. So in what context? So if
in a generalized context, sir.
In a generalized context, when you look at a control bug, see, in any RTL design, you have two different blocks. One is a data path block, and the other one is a control block. So if you take a simple multiplier, right? So the multiplier requires, right, an addition of two numbers. So two for, let's say, for example, A and B signals, right, requires two registers, and the contents of these two registers are added into a particular register, a third register, right? And when we need to control the first register data, and when we need to control the second register data, and so when we need to enable the third register, all these signals will be passed through a control block. So when you are going through a multi-clock domain, so when this control signal is passing through, right, a multi-clock domain and reaching to a particular block, particular combo logic, so then definitely this control logic will go through a metastable state. So will there be a loss of data? Instead of 1, it might report a 0. Instead of 0, it might report a 1. So these bugs need to be identified. So it might be a data bug or it might be a control bug.
Thank you, sir. So can we use asynchronous FIFO to rectify the CDC problems?
Exactly, right. So which I have mentioned, right, earlier with the two different protocols. So one is the handshaking and the other one is FIFO. This FIFO is nothing but an asynchronous. Asynchronous, right? Synchronous FIFOs will not work, right, for addressing to these issues. Only asynchronous FIFOs will work because asynchronous operates with a different write clock frequency domain and a read clock frequency domain. So therefore, we can make use of right, asynchronous FIFOs to address these right CDC issues.
Thank you, sir. So finally, could you please tell us about any open source tools that are there with respect to CDC?
So CDC is a bit difficult.
Okay,
It's a tough question it's a tough question in VLSI, right?
Okay.
To get the open source tools, especially for this CDC. For the rest of the things, either, right, if you want to go for a very low verification, right? So you might get the open source tools, but so especially for this one, right, it is very bit difficult to get the open source tools.
Thank you, sir. Thanks a lot. It was a very innovative session, and thanks a lot for your patience and such a insightful presentation.